Hey, it's David. Every week I post a math problem here on YouTube and over on my Twitter account. Then I post a video with a solution, just like the one you're watching now. The questions are meant to be approachable by anyone who has knowledge of high school level algebra. If that sounds like something you're interested in, then feel free to join along with these weekly recreational mathematics challenges. Let's dive into last week's problem. And don't forget to watch to the end of the video to see what this week's problem is. Last week's problem was about divisibility. Here's how the problem goes. How many ways are there to fill in the blanks for the number 5 blank 3 blank 1 blank 6 7 2 with the digits 4, 9, and 8 in some order so that the resulting number is divisible by 792? One thing to keep in mind is that you have to fill in each blank with a unique digit. So you couldn't fill in all the blanks with an 8, for example. If you put a 4 in the first blank, then you need to put an 8 or a 9 in the second blank, and then whatever number is remaining in the last blank. Now's a good time to pause the video and see if you can solve this if you haven't attempted already. Or just keep watching to see my solution. I'm actually going to give two solutions to this problem. The first one uses brute force. That is, we'll figure out how many ways there are to order the digits 4, 9, and 8. Then we'll plug those orderings into the blanks for the number and check whether or not that resulting number is divisible by 792. So how many ways are there to order three numbers? This is a classic counting problem, and the solution is given to us by something called the product rule. The rule states that if there are X ways of doing one task and Y ways of doing another task, then there are X times Y ways of doing both tasks. You can extend this to any number of tasks. So if I have 3 tasks with X, Y, and Z ways of doing each task respectively, then there are X times Y times Z ways of doing all 3 tasks. In our problem, a task is filling a blank with a number. Since there are 3 blanks to fill, there are 3 tasks. And there are 3 ways to fill the first blank. We can either fill it with a 4, a 9, or an 8. Once we filled in the first blank, there are 2 ways to fill in the second one, since we have to use a unique number and we've already used one of the 3. Finally, the third blank can only be filled in one way, since 2 of the 3 numbers were used to fill in the other 2 blanks. So according to the product rule, there are 3 times 2 times 1, or 6 ways to fill in the blanks. Now, you could work out the 6 different ways by hand, but I like to code things in Python. So let me show you how to do that. The first thing you need to do is import the itertools module from the Python standard library. Inside of itertools is a function called permutations. This function takes a list of objects. For us, those objects are the numbers 4, 9, and 8, and returns an iterator over all possible orderings of those objects. If you don't know what an iterator is, you can think of it as an object that's used to access items in a collection one item at a time. It's not the same thing as a list or tuple in Python though, but you can convert an iterator to a list, for example, using the list function. I'll throw a link to a good resource on iterators in the video description for those of you that are interested. Here you can see all 6 possible orderings for the numbers 4, 9, and 8. Now that we have those, we can plug them into the blanks in the number and check whether or not the resulting number is divisible by 792. Start by creating a string with the digits of the number and underscores in the positions where the blanks are. I'll call that string number with blanks. I'll also create an empty list called valid orderings, where I'll store any orderings that make the resulting number divisible by 792. Then we'll loop over all of the orderings for 4, 9, and 8 that we got from the permutations function. Inside of the loop, we'll convert the number with blank string to a list and call that number list. The indices of the list that have the underscores in them are 1, 3, and 5. That's because lists in Python are 0 indexed. The first element in number list has index 0, the second element has index 1, and so on. Since we know the indices in the list for the underscores, we can replace each of those with a number from the ordering. So we'll assign the first value of the ordering to list index 1, the second value to list index 3, and the third value to list index 5. Notice that I'm adding each of these values to the list as a string. That's because all the values in number list are also strings. When I converted number with blanks to a list, it made a list of all the characters in the string. And characters are also strings. Now I can convert the number list with all the blanks filled in into an integer. First, I need to join all of the characters in number list together using the string join method. I use an empty string to call join from so that all of the characters just get squashed together without any space between them. Then I wrap the whole thing with a call to the int function. which converts the string of numbers to an integer and assigns that integer to the variable resulting number. To check if a number is divisible by 792, I use the percent operator, also called the modulo operator. This returns the remainder of dividing the number on the left side of the operator by the number on the right side of the operator. So if resulting number is divisible by 792, then the result of taking the modulo with 792 will be 0. And if resulting number is divisible by 792, then I'll append the ordering to the valid orderings list. Once I execute this, I can look at how many orderings were added to valid orderings. And there are 6. All 6 possible orderings are valid, so we've solved the problem. A couple of quick notes on the solution. First, we didn't need to convert orderings to a list. You can loop over the iterator returned by permutations, but by converting it to a list, it allowed me to show you what the orderings are. Second, this brute force method works fine for us because there are a small number of possible orderings. If there had been a really large number of orderings, say, for example, a huge number with billions of blanks in it, then looping over all those orderings would have been really time consuming. And solving the problem like this doesn't really tell us why all 6 orderings worked. So let's take a look at a second solution that uses divisibility rules. There are a number of tricks you can use to test whether or not one number is divisible by another one. For example, you can tell if a number is divisible by 2 by looking at whether or not the last digit is even. And you can tell whether or not a number is divisible by 10 by checking if the last digit is a 0, or divisible by 5 by checking if the last digit is a 5 or a 0. But how do you discover these rules? It all comes down to how we write numbers in the first place, with base 10 being the most common base we use to write numbers. Let's look at the number 4,581. We can break this number up into parts. The 4 is in the thousands place, or 10 to the third power. The 5 is in the hundreds place, or 10 to the second power. The 8 is in the tens place, or 10 to the first power. And the 1 is in the ones place, or 10 to the 0th power. Let's look at what happens when we divide each part by 2. Specifically, we want to look at the remainder that's left over when we divide each part. 4 times 10 to the third power is 4,000, and the remainder when divided by 2 is 0. The same is true for 5 times 10 to the second power, which is 500, and 8 times 10 to the first power, which is 80. The only part of the number that has any chance of leaving a non-zero remainder when divided by 2 is the digit in the ones place. In this case, 1 times 10 to the 0th power is 1, which has a remainder of 1 when divided by 2. Nothing about the digits 4, 5, or 8 is used when looking at the thousands, hundreds, and 10 places. No matter what those digits are, they're multiplied by numbers that are divisible by 2, so any digit in those places will result in a number divisible by 2. This leads us to the rule that says a number is divisible by 2 whenever the last digit, the one in the ones place, is even. We can do the same kind of process to see whether or not a number is divisible by 3. If you divide any power of 10 by 3, you're left with a remainder of 1. Pause the video and think about that for a second. Can you convince yourself that what I just said was true? The consequence of this is that you can tell whether or not a number is divisible by 3 by checking whether or not the sum of its digits are divisible by 3. Going back to our example of 4,581, we start with 4 times 10 cubed, which is 4 times 1,000, which is 4 times 1 plus 999, which is 4 plus 4 times 999. Then we have 5 times 10 squared, which is 5 times 100, or 5 times 1 plus 99, or 5 plus 5 times 99. Then 8 times 10 to the first power is 8 times 10, or 8 times 1 plus 9, or 8 plus 8 times 9. And finally, 1 times 10 to the 0th power is 1. We can rearrange this sum into 4 times 999 plus 5 times 99 plus 8 times 9 plus 4 plus 5 plus 8 plus 1. The first 3 terms are all divisible by 3, so the whole sum is divisible by 3 as long as 4 plus 5 plus 8 plus 1 is. Since 4 plus 5 plus 8 plus 1 is 18, then we know that the number 4,581 is divisible by 3. Now let's see how we determine whether or not a number is divisible by 6. Well, 6 is 2 times 3, and if a number is divisible by 6, it must be divisible by 2, and also divisible by 3. So first we check whether or not the number is divisible by 2 by looking at the last digit and seeing whether or not it's even, and then we check if the number is divisible by 3 by adding up all the digits and seeing if that number is divisible by 3. But how does all this help us solve the challenge problem? First, let's take a look at the number 792. How could we break this up into a product of numbers? Well, 792 is divisible by 2, since the last digit is even. And if we divide 792 by 2, we get 396. 396 is divisible by 2, and if we divide that by 2, we get 198. And 198 is divisible by 2, and dividing 198 by 2 gives 99. Now, 99 isn't divisible by 2 anymore, so we can write 792 as 99 times 2 times 2 times 2. Well, what about 99? That's divisible by 3, and dividing 99 by 3 gives 33. 33 is also divisible by 3, and dividing by 3 gives 11. So 792 is equal to 11 times 3 times 3 times 2 times 2 times 2. 11 is a prime number, so we can't divide it by anything. What we've done is find the prime factorization of 792. That is, we've broken 792 up into a product of prime numbers, since 11, 3, and 2 are all prime. Now we can collect like terms in the factorization and write 792 as 8 times 9 times 11. So if the number 5 blank 3 blank 1 blank 672 is divisible by 792, then it must also be divisible by 8, 9, and 11. And if it isn't divisible by any one of those numbers, then it can't be divisible by 792. Now, here are the rules for checking whether or not a number is divisible by 8, 9, and 11. I'll state them here without any kind of proof, but if you feel up to it, you should try and derive those rules for yourself. A number is divisible by 8 if the last 3 digits of the number are divisible by 8. And a number is divisible by 9 if the sum of its digits are divisible by 9. Finally, a number is divisible by 11 if the alternating sum of its digits is either 0 or a multiple of 11. What do I mean by alternating sum? Well, take the first digit, then subtract the second digit, then add the third digit and subtract the fourth, and so on and so on. If the number you get after doing all that is 0 or some multiple of 11, then the original number was divisible by 11. So let's use these rules to see what happens with the number 5 blank 3 blank 1 blank 672. The last 3 digits are already given to us. They're 6, 7, and 2. So we need to check if 672 is divisible by 8. You could do this in your head or work it out on a piece of paper, but a quick check with Python tells us that 672 is in fact divisible by 8. What about divisibility by 9? Well, that depends on what numbers we put into the blanks, right? But notice that the order that we put numbers into the blanks doesn't matter because we're just summing all of the digits. And no matter what order we sum those in, we're still going to get the same number. That's the important bit here. And what about 11? We start with 5, then subtract whatever number's in the first blank, then add 3, subtract whatever number is in the second blank, add 1, subtract the number in the third blank, then add 6, subtract 7, and add 2. Notice that all 3 blanks end up getting subtracted. So again, the order of how we put numbers in those blanks doesn't affect the final alternating sum. Those numbers always get subtracted, and the order we subtract them in doesn't matter. So what this tells us is that however we fill in the blanks, the number will always be divisible by 8, and the divisibility by 9 and 11 doesn't depend on the order that we filled the blanks in. So we only need to test one ordering of the numbers 4, 9, and 8. If that order results in a number divisible by 792, then all of the orderings will. And if it doesn't result in a number divisible by 792, then none of the orders will. Let's put a 4 in the first blank, 8 in the second blank, and 9 in the third blank. I've done this in a string, but I really want to get this as a list of digits. So I'll use a Python list comprehension to build a list of digits, casting each character in the string to an integer with the int function. I can inspect the number list variable to see that I do in fact have a list of digits now. To check if the number is divisible by 9, I can use the sum function to add up all the elements of the list, and then use the modulo operator to see if I get 0 when I reduce modulo 9. And I do. Finally, to check if the number is divisible by 11, I first add up all the numbers that have an even index. And I can do this using this funny looking slice on the Python list. This runs through the list starting at index 0, but skips every other index. So it sums up the numbers with even indices. Then I subtract from that the sum of the numbers at odd indices, and look at the whole thing reduced modulo 11. That gives me 0, telling me that the alternating sum of digits is divisible by 11, and therefore the original number is divisible by 11. Since the number is divisible by 8, 9, and 11, it's also divisible by 792. And since we determined any ordering of 4, 8, and 9 would work to fill in the blanks, we know that every ordering will work. The solution to this week's problem might feel a little bit different to some of the other solutions in the series. I didn't write a function or a program that gives a general solution. Keep that in mind when you're submitting solutions for future problems. You don't need a polished solution. The idea here is to think about how we can use Python or any other programming language to help us investigate mathematical concepts. And hopefully in doing so, we'll learn a little bit about programming, learn a little bit about math, and get better at both. This week I had 3 solutions sent to me, and you can find links to all 3 of those solutions down in the video description. One solution that I want to feature though comes from Michael Dornbos. And Michael, I hope I pronounced your name correctly. Feel free to roast me in the comments if I didn't. Michael solved this problem using the brute force method, but he did it on some vintage computers. He used a VIC-20 and an Atari 400, and he wrote the program using BASIC. Michael also submitted a solution to the first challenge that I posted in this series, and he did that one on a Commodore 64. He wrote up the whole thing on an awesome blog post, which I'll share the link to in the video description. In that blog post, he shares the basic code that he wrote and some video of his solution actually running on the Commodore. It's pretty awesome, so make sure to check that out. Thanks to everyone who submitted solutions. Please, keep them coming. Next week's problem continues with the divisibility theme, and it's a 2-parter. Here's how it goes. Part A. For each value of n from 2 to 16, find the largest and smallest 9-digit numbers containing each of the 9 non-zero digits exactly once that are exactly divisible by n. So something like 1, 2, 3, 4, 5, 6, 7, 8, 9 is a 9-digit number using each digit exactly once, but 1, 2, 2, 3, 4, 5, 6, 7, 8 isn't because 2 is repeated, and 1, 0, 3, 4, 5, 6, 7, 8, 9 isn't because you aren't allowed to use 0. Part B is to do the same thing for 10-digit numbers containing each of the 10 digits, including 0, exactly once. And note that 0 can't be the first digit of a number. There are a couple different ways to submit solutions. You can open a pull request or an issue on the companion GitHub repository for this series. Either one will work, and the link to the GitHub repository is down in the video description. Or you can email your solution to me at recmath@davidamos.dev. If you want to work on a solution, but you don't know how to translate it to code, or you just don't care about coding at all, that's completely fine. I'm happy to look at those solutions as well. So feel free to write it up and submit it via email. I'll pick 1 or 2 solutions that I think are awesome and feature them in next week's video. Thanks again to everyone who submitted solutions this week. And thanks so much for watching. I'm David Amos, and I'll see you in the next video.